In this video, we're going to begin a discussion of register allocation, which is one of the most sophisticated things that compilers do to optimize performance, and also involves many of the concepts that we've been discussing in global flow analysis. Recall that intermediate code can use unlimited numbers of temporaries, and this simplifies a number of things. In particular, it simplifies optimizations because we don't have to worry about preserving the right number of registers in the code. But it does complicate the final translation into assembly code because we might be using too many temporaries. And this is actually a problem in practice. So it's not uncommon at all for intermediate code to use more temporaries than there are registers on the target machine. The problem then is to rewrite the intermediate code to use no more temporaries than there are machine registers. And the way we're going to do that is we're going to assign multiple temporaries to each register. So we're going to have a many-to-one mapping from temporaries to registers. Okay? And clearly there's a little bit of an issue here. If we really are using many temporaries, we will not be able to fit them all into a single register. So there needs to be some kind of a trick, and we'll say what that trick is in a few minutes. And there'll be situations actually when this will fail and we'll have to have some kind of backup plan. But our default plan is to try to put as many temporaries as possible into the same machine register, and doing all this without changing the behavior of the program. So how can we do this magic thing? How can we actually make a single register hold multiple values? Well, the trick is that it's fine for a register to have multiple values as long as it only has one value at a time. So let's consider this program, and I'm going to switch colors here. Okay, it's a simple three-statement program. And notice here that A is used in the first two statements, so it's written in the first statement, read in the second statement. E is written in the second statement and read in the third statement, and F is only written in the third statement. And actually these three values, A, E, and F, they don't ever really coexist at the same time. By the time we've read A, we're really done with it. We've had all the uses of A we're going to have in this little code fragment. Here I'm assuming that A, E, and F are not used anywhere else. And so it turns out that A, E, and F could all actually live in the same register. All right, and that's assuming that A and E are dead after their uses. And what would that look like? Well, let's allocate them all to a particular register, R1, and let's assign C, D, and B each to their own individual registers. Then the code would look like this. R1 would be R2 plus R3, and then R1 would be R1 plus R4, and R1 would be R1 minus 1. All right, so now notice how this is just a transliteration of the code over here into registers, but there is a many-one mapping of names on the left to register names on the right. Now, register allocation is an old problem. In fact, it was first recognized way back in the 1950s in the original Fortran project. But originally, register allocation was done with fairly crude algorithms, and it was rapidly or very quickly noticed that this was actually a bottleneck in the quality of code generation, that actually limitations on the ability of register allocation to do a good job had a really significant effect on the overall quality of the code that compilers could produce. And then about 30 years later, in 1980, a breakthrough occurred where people discovered, or a group of researchers at IBM discovered a register allocation scheme based on graph coloring. And the great thing about this scheme is that it's pretty simple, it's easy to explain. It's global, meaning it takes advantage of information from the entire control flow graph at the same time, and it also happens to work well in practice. And here's the basic principle that underlies the modern register allocation algorithms. So if I have two temporaries, T1 and T2, I want to know when they can share a register. So they're allowed to share a register, they're allowed to be in the same register if they are not live at the same time. Okay, so if at any point in the program, at most one of T1 or T2 is live, and the more concise way, which I already said at least partially, is that if T1 and T2 are live at the same time, okay, meaning that there's some program point where both are live, then they cannot share a register. All right, so this is the negative form of the statement. And it just tells you that if you need two values at the same moment in time, then they have to be in separate registers. Let's take a look at a control flow graph, and now we know that in order to do the register allocation, to solve the register allocation, at least in this way, we're going to need liveness information. So let's compute the live variables for each point of this program. So here it is, and I'll just walk through it very quickly. Let's assume that on exit from this loop that only B is live. So B is the output of this piece of the code, and it's used elsewhere, but none of the other variables are live. So then if we work backwards, remember that liveness is a backwards analysis, we'll see here that B is written, and so it's not live before this statement, but F and C are read. So both C and F are live before this basic block. Okay, and similarly, if we go up another level here we see that E is now live and F is dead because F was written here and E was read. And over on this path, here we have another exit where B is live. And now at this point here, right after this basic block, the set of variables that are live is B, C, and F, because B is live on one path and C and F are live on the other path. Remember, for something to be live, it only has to be live on in some future possible evolution of the execution. So on some path out of this node, if a variable is live, then it's live at the exit from this node. All right, working backwards here, B, C, E, and F are live here because E is read, and B, C, and F are not referred to in this statement, and so they just propagate upwards. Here, B is removed from the live set because it's written, but D is added in this set here, and similarly for the other edges in this graph. And if you go and check all the other edges, you will see that the live set is correct, and it just follows from the simple rules we gave in the previous video. Now, how are we going to use the liveness information to do register allocation? Well, we're going to construct an undirected graph, and in this graph there will be a node for each temporary, so each variable will have a node in the graph, and there'll be an edge between two temporaries if they are live simultaneously at some point in the program. All right, so backing up and looking at our little example here, we can see, for example, at this point in the program, C and E are both live. They're both in the live set after this basic block executes. So C and E cannot be in the same register. All right, continuing on. This data structure, this graph, is called the register interference graph, or RIG for short. And again, the basic idea is that two temporaries can be allocated in the same register if there is no edge connecting them in the register interference graph. So here's the register interference graph for our example. This is the graph constructed from the code and the liveness analysis that were given a few slides ago. And it's easy to read off from the graph what the constraints are. So for example, B and C cannot be in the same register because B and C are connected by an edge. Okay, it's saying that they're live simultaneously at some point of the program, and so they have to live in different registers. On the other hand, notice that there is no edge between B and D. Okay, so this edge is missing, and therefore it's possible that B and D could be allocated in the same register. Their live ranges, or the times at which they are live, do not overlap. So the great thing about the register interference graph is that it extracts exactly the information needed to characterize the legal register assignments. So it gives us a representation of all the possible legal register assignments. Now, I haven't said how we actually get a register assignment out of the register interference graph, but the first step is to characterize the problem in some kind of precise way. And the graph of cannot live in the same register constraints does that for us. The other thing that's good about it is that it gives a global view of the register requirements, meaning it's over the entire control flow graph. So it takes into account information from every part of the control flow graph, which will help us to make good global decisions about what values are important to live in registers. And finally, the other thing to notice is that after reconstruction, the register allocation algorithm is architecture independent. Now, I haven't shown you the algorithm, so you just have to believe this statement for the moment. But it's going to turn out that we're not going to depend on any property of the machine except for the number of registers. That's the only thing we'll need to know about the machine in order to take a rig and do register allocation using it.